Now the time has come to apply our ideas of L'Hopital's rule to different types of indeterminate forms besides 0 over 0 and infinity over infinity. And we're going to start with type 2, which is when we have infinity minus infinity and 0 times infinity. So of course we're going to have to use algebra tricks first because we need to turn them into 0 over 0 or infinity over infinity. That is a requirement for L'Hopital's rule. It has to be one of these two forms. It cannot be used unless it is in one of those forms. All right, so let's look at how we started this problem. So if we want to check our form here, and what form are we in? All right, so if I'm going to let x go to infinity, then this is infinity times the natural log of 1 plus 1 over infinity. Now 1 over infinity is 0. That's not indeterminate. So that's infinity times the natural log of 1, which is infinity times 0. That is indeterminate. Right? We don't know what that is. Okay, it's one of our 7 indeterminate forms. Okay, so we are going to use algebra. Right? So algebra trick number 1. Take the limit as x goes to infinity. I'm just going to say algebra trick. All right, I'm going to take the natural log of 1 plus 1 over x. I'm going to divide it by, and here's what I'm going to do. X there is the same as 1 divided by x in the denominator. For the same reason that we had that trick a page ago where we had like the 1/7 and the 1/3 and divided. So x over 1 is the same thing as 1 divided by 1 over x. I'll make a little note. It's an algebra note. X over 1 is the same thing as 1 divided by 1 over x. So we're using this trick. We're going from x to 1 divided by 1 over x. Sneaky, huh? All right, so that's the trick I'm using. Make sure you make a note of it because you'll use this one a lot. And this is very frequent, right, that we will use this algebra trick. I'm just going to star it because you're going to use it often. All right, so then now let's check my form. Right, so that little trick, let's check it. So I still have the natural log of 1 plus 1 over infinity on the top, then I have 1 over infinity on the bottom. The natural log of 1 plus infinity is the natural log of 1, because that's 0, divided by 0, which is 0 over 0. Yay! That makes us happy because that means that we can use L'Hopital's rule. All right, so my next step would be to say, okay, then by L'Hopital's rule, this is equal to the limit as x goes to infinity of, and now we have to find derivatives. Okay, so looking at our numerator here, just for the heck of it, I'll do it in blue. The derivative of this is 1 over 1 plus 1 over x times the derivative of the inside. Now the derivative of 1 is 0, but the derivative of 1 over x, that's really x to the negative 1. So that'd be negative x to the negative 2. Similarly, the derivative in my denominator, right, because that's x to the negative 1, would be negative x to the negative 2. Oh, that's convenient because those two are the same value, right? So they divide away to nothing. And that means, and this is not L'Hopital's rule, so I don't put a L'Hopital over this because I'm just simplifying here. That's the limit as x goes to infinity of 1 over 1 plus 1 over x. That's the only part that's left. But that's not indeterminate. I can actually find that. That's 1 over 1 plus 1 over infinity. That would be 1 over 1 plus 0, which is 1 over 1, which is 1. I'm belaboring the point there. we knew it was 1, probably 2 steps ago, but there you have it. And sure enough, if you look at this graph, you can see that we're approaching y equals 1 as x goes to infinity. And of course, I can verify that on Desmos. So here's my function, x times the natural log of 1 over 1, or 1 plus 1 over x. And then as x gets larger and larger, you can see that y value is approaching 1, 9.98, 0.9804, etc., etc. So it's verified graphically. And y equals 1 is actually a horizontal asymptote, in case you're interested. All right, so now let's do a different problem. So let's look at the limit as x goes to infinity of x minus the square root of x squared plus 1. All right, so let's check our form just a little bit here. Check form. I think I know where this is going, but that's all right. So it'd be infinity minus the square root of infinity squared plus 1, which is infinity minus infinity. All right. So trick number 1. We're going to apply some things. Actually, I'm going to call it trick number 2 because I'm actually going to use the same trick. Well, I'll do it trick number 1 here. So this is just an algebra trick that I'm about to apply. So algebra trick number 1. Let me remind you of some things here. If I have the square root of a squared plus b squared, that's equal to the square root of a squared times 1 plus b squared over a squared. You can factor, in other words, which would be a square root of 1 plus b squared over a squared. Sneaky, huh? Okay, so that's what we're going to use. So we're going to use algebra trick number 1. Algebra, there we go. Trick number 1. So this is the limit as x goes to infinity, x minus, there's a squared, there's b squared. So I'm going to factor it. I'm going to say, hey, that's x squared times 1 plus 1 over x squared. Now, why am I doing all this? Well, because I really want that 1 over x squared, because that's not indeterminate. 1 over infinity is 0. See what I'm doing? So I'm applying algebra trick. Actually, I should say this. That'll be easier just for you guys to see. There you go. Because it's really, I'm going to show both steps. So this is the limit as x goes to infinity of x minus x square root 1 plus 1 over x squared, like that. Okay, so there's algebra trick number 1. I could factor an x out of both of these. So this is the limit as x goes to infinity of x times 1 minus the square root of 1 plus 1 over x squared. In other words, I just factored x out of both of those terms. Sorry, that was a little too small. There we go. I mean, I can check form if you want. I mean, it isn't really going to change anything. So this is infinity minus infinity times 1, right? So this is still infinity minus infinity right here. This is now infinity times 1 minus 1, so infinity times 0 now, right? Which is also indeterminate, right? So this was infinity minus infinity. This is infinity times 0. That's my form. I still can't use L'Hopital's rule, right? But I remember that trick from before. We had infinity times 0 in the last problem, and I can take this and use algebra trick number 2. So this is the limit as x goes to infinity of 1 minus the square root of 1 plus 1 over x squared over 1 over x. So that's algebra trick number 2. It's the same one as the previous page. X over 1 is the same thing as 1 over x. Same trick we used before. All right, now let's check my form. This is 1 minus square root of 1, right? Because that's 0 right there. So my form now is 0 divided by 1 over infinity is 0. Yay! Right? Now with this second algebra trick, I've got 0 over 0 finally, and that means that I can use L'Hopital's rule. So that means that I can say, hey, by L'Hopital's rule, this is equal to the limit as x goes to infinity of, all right, I'm going to have to take the derivative of all this, right? So the derivative on the denominator is easier because that's negative x to the negative 2. The derivative of 1 is 0, no problem. Remember that what you're doing is you're taking the derivative with respect to x of 1 plus, well, negative 1 plus 1 over x squared to the negative, or excuse me, to the 1/2, like that. So you'd bring the half down, right, because that's a square root. Square root is a 1/2 power. So it'd be negative 1/2, and then leave the stuff inside, 1 plus 1 over x squared to the negative 1/2 times that by, and now take the derivative of the inside. Well, the derivative of 1 is 0, so that's out. And then this is x to the negative 2, so that'd be negative 2x to the negative 3. Right? Matter of fact, I could even write it like that over here, just so you can see. So this is x to the negative 2. Right? That's what we're really doing for that numerator up there. And the denominator is even easier, right? Because it was x to the negative 1, the derivative of x to the negative 1 is negative x to the negative 2. So that's easy, right, for that one. And then this one is that whole numerator bit. Okay. I don't think I need to write that there. I think you get it. Okay, so, well, I need to use some algebra. All right, so the negative 1/2 and the 2, negative 2. So this one and this one kind of cancel each other out. And they cancel the negatives too, because negative times a negative makes it positive. That's lovely. Negative powers really belong in other places. So these two things with the negative powers can go down, and this one with the negative power can go up. So that would make it equal to the limit as x goes to infinity of negative x squared. See, that one comes up. X cubed goes down. 1 plus 1 over x squared to the 1/2 goes down. Well, squared and cubed, that's going to go and leave me just an x down here. So this is the limit as x goes to infinity. All that's left up here is a negative 1. When I divide like that, there's a 1 still left in there. And then there's an x square root 1 plus 1 over x squared. All right, now let's finally put infinity in and see what happens, because I don't have infinity over infinity. Hopefully I won't have one of my other weird forms. This is negative 1 over infinity times the square root of 1 plus 1 over infinity squared. Well, 1 over infinity is 0, so this is negative 1 over infinity times the square root of 1 plus 0. That's infinity. So this is negative 1 over infinity, which is 0. Because we know that any constant divided by infinity is 0. That is not indeterminate. And of course, you can see it right on the graph. Right? Y equals 0 is a horizontal asymptote. It's verified graphically. Right? As x gets larger and larger, the y value is going closer and closer to 0. Of course, we can double check that in Desmos for ourselves. It's very nice of Desmos to do us. And we can see, sure enough, that 0 is in fact that horizontal asymptote. Anything higher than that is too high, but 0 is just right. And we can see that that curve is getting closer and closer to 0 as x increases.